Hello, this is the section 3.6 lesson. Sometimes in a random experiment there's more than one random variable that we might be interested in, and we may want to know a probability of some combination of those random variables. And so to calculate such probabilities, we're going to use this idea of joint distributions. And we're going to start off talking about discrete random variables and a joint probability mass function, or joint PMF. A joint PMF is described by the function little f. Little f of xy is defined to be the probability that x equals little x and y equals little y at the same time. So to illustrate this idea, let's consider this simple example. Suppose we have a bag that contains a 1-ounce marble, a 2-ounce marble, and a 3-ounce marble. And in our random experiment, we're going to choose 2 marbles with replacement. So our sample space consists of outcomes that look like this. Maybe we get the 3-ounce marble followed by the 1-ounce marble. Or we get the 2-ounce marble followed by the 3-ounce marble. Or maybe we get the 3-ounce marble and then the 3-ounce marble again. So there's a total of 9 outcomes in my sample space. So the 2 random variables we're going to deal with here are x, which is the weight of the heavier marble, and y, which is the weight of the lighter marble. So let's calculate a couple of values of the joint PMF. So for instance, let's do f of 1, 1. By definition, that's the probability that x equals 1 and y equals 1 at the same time. Or in other words, it's the probability that the lighter marble weighs 1 ounce and the heavier marble weighs 1 ounce. Well, that can only occur when both marbles I get weigh 1 ounce. So there's only one outcome in which both x and y equals 1. So the probability of that happening is 1 divided by the size of my sample space, so 1/9. Let's calculate f of 2, 1. So that's the probability that the heavier marble weighs 2 ounces and the lighter marble weighs 1 ounce. Well, that can happen when I get the 1-ounce marble and then the 2-ounce marble, or the other way around, the 2-ounce marble followed by the 1-ounce marble. So there's 2 outcomes for which x equals 1 and y equals, or x equals 2 and y equals 1. So 2 divided by the size of the sample space, that's 9. Another example, let's calculate f of 1, 2. So by definition, that's the probability x equals 1 and y equals 2. So that means the heavier marble is 1 ounce and the lighter marble is 2 ounces. Well, that's impossible to happen, and so that probability is just 0. So we can summarize all the values of our joint PMF in a table such as this. So across the top we list our values of x, 1, 2, 3. Across the side the values of y, 1, 2, 3. And in the middle we list the values of the joint PMF. Now these numbers here on the right column and the bottom row we'll talk about in a minute. So there's our joint PMF described in the form of a table. So now we might also ask a question about just the heavier marble, for instance. We might ask, what's the probability that the heavier marble weighs 3 ounces? Maybe we're not interested in the lighter marble at this point in time. We just know something about the heavier marble. And so a question like this motivates our definition we call the marginal distribution. So the marginal distributions of x and y are denoted this. So we have little f sub x of x, which is defined to be the probability that the random variable x equals the number little x. So that we call the marginal distribution of x. And then likewise we have the marginal distribution of y. F sub capital Y of little y is defined to be the probability that capital Y equals little y. And so to illustrate how to calculate a value of the marginal distribution, let's consider the marginal distribution of y at 1. So that is by definition the probability that capital Y equals 1. So think about how can that happen. Well, that could happen if x equals 1 and y equals 1, or x equals 2 and y equals 1, or x equals 3 and y equals 1. And so those outcomes are all disjoint, and so we can add up their individual probabilities. So the probability that x equals 1 and y equals 1 is little f of 1, 1. Likewise, this is little f of 2, 1, little f of 3, 1. And then we just read their values off the table. F of 1, 1 is 1/9. F of 2, 1 is 2/9. And then f of 3, 1 is also 2/9. And we add those up, and we get 5/9. So that is the probability that y equals 1. Now, if you note what we did here to calculate that probability is we simply added up the numbers in this row, and we put that sum over here in this right-hand column. Likewise, if we want to find the probability that y equals 2, we can add up these numbers, and we'll put that sum there. If we want to find the probability that y equals 3, we'll add up those numbers, and we put the sum there. And then, by similar arguments, if we want to find the probability that x equals 1, we'll add up those numbers. We'll write our sum there. Probability x equals 2, we add up those numbers. Probability x equals 3, we add up those numbers. And so we write our values of the marginal distributions here along the margins of this table. That's where the term marginal distributions get its name. So now we're going to give a little more formal definition of the joint PMF and the marginal distributions. And so this starts off by saying let's let r sub x denote the range of x and r sub y the range of y. So then rx cross ry is the set of all possible values of x and y. So then the joint PMF is a function that satisfies these three properties. First property says simply that every value of f has to be between 0 and 1. Second property says that when we add up the values of the joint PMF over all values in this set R, that should equal 1. And then the third property really tells us how we're going to use the joint PMF. It says to calculate the probability that x and y take on some values in a set, we're going to add up our joint PMF over all values of x and y in the set. Now, we've given a formal definition of our marginal distributions as this. So the marginal distribution of x, is this, and we can find that by adding up the values of the joint PMF over all values of y. Likewise, the joint or the marginal distribution of y is we add up our joint PMF over all values of x. So to illustrate the calculations of marginal distributions and use of a joint PMF, let's consider this this joint PMF given here. So we have our two random variables x and y. X has range 1, 2, and y has range 1, 2, 3. And here's the joint PMF given in the form of a formula. So let's calculate the marginal distribution of y. And so by definition, what we're going to do is add up the joint PMF over all values of x. So in formal notation, we're going to evaluate this. So we're going to plug in x equals 1 and then x equals 2. Do that arithmetic, simplify it, and there's our joint our marginal PMF for y. Likewise, for the marginal PMF of x, we're going to add up our joint PMF over all values of y. So we're going to plug in y equals 1, then y equals 2, then y equals 3. Do that arithmetic, and there's our marginal distribution of x. Now, let's calculate a probability. Suppose we want to calculate the probability that x plus y is greater than or equal to 4. Okay? So what we're going to do is add up our joint PMF over all values of x and y that satisfy this inequality. So in formal terms, this is what we're going to evaluate. Now, in more informal terms, what we can do is simply look at every single pair of values of x and y and ask ourselves, does that pair satisfy this inequality that x plus y is greater than or equal to 4? If it does, then we're going to plug that pair into our joint PMF and add them up. If not, then we're not going to plug them in. So if we look at the first pair, 1 and 1, we say, does 1 plus 1 greater than 4? No, it's not, so we're not going to deal with it. Next pair, 1 and 2, does 1 plus 2 greater than or equal to 4? No, it's not, so I'm not going to worry about it. Next one, 1 and 3, well, yeah, that sum is 4, so I'm going to plug those values into my joint PMF. I look at my next pair, 1 and 2, nope, sum is only 3. Next one, 2 and 2. Yes, the sum is 4. So we're going to plug those in to our joint PMF. And the last pair, 2 and 3. Yeah, the sum is greater than 4. So we're going to plug those in. And then we add up those three different values of the joint PMF. And there's our probability, 43 over 54.